In 5.5 part 2, you're going to see inequalities that require some algebraic steps to be made. I'm going to show you 3 examples, and then I will also show you an example of how to check to make sure that your solutions are correct. So all of these 3 and all of the practice problems you're going to work with are either one-step inequalities or two-step inequalities, meaning you will either need to do 1 move or 2 moves to solve them. This first example, A, is an example of a one-step inequality. So our question is, what is the solution set for x minus 1 is greater than 6? In other words, what are the values? I want to highlight that values. When working with inequalities, we have infinite possibilities and infinite solutions in our solution set. So what are the values that make this statement true? I'm going to write both an inequality statement and graph our solution on a number line. So I'm going to set this up exactly like I would an equation. I'm going to say x minus 1 is greater than 6. The only thing I'm going to do differently here than I would setting up an equation is I'm not going to use a t-chart because I find that t-charts kind of muddy up the work with the inequality symbols sometimes. But I do still want to organize my work so that my inequalities stay directly underneath the original one as we work. And here I'll draw that so it looks a little more clear. Okay, so this is a one-step inequality, so there's only one thing we need to do. And our goal is the same with inequalities. We're trying to get all of our variables on one side of the inequality and all of our constants on the other. So in this case, the only thing we need to do is move that -1. So we're going to use our inverse operations. We're going to take the additive inverse and make a 0 pair there. Let's add 1. We have to add 1 to both sides, just like an equation, to keep the statement true. So once I've added 1 to both sides there, I have my positive x left over here, and saying that that has to be greater than 7. X plus 1 is 7. So let's graph this guy. So you're going to have these blank number lines to work with, and I'm just going to put my boundary right in the middle. So 7 is my boundary. 7 is that boundary where this statement either becomes true or untrue. And since 7 cannot be a part of my solutions because this is not x is greater than or equal to, it is just x is greater than, put my open circle. And then since x has to be greater than 7, all numbers greater than 7. And a student did point out to me once, they noticed that this symbol right here matches the direction on the number line you need to go. I thought that was pretty cool. So we do want to put a little more data in here just so we have a complete number line. So I'm going to put 6 there, 5, 4, and then 8, 9, 10, and so on, just to show where my solution set lies. All numbers greater than 7. Okay, let's try another one. This is another one step. In this case, we're looking for the solution set for 2x is less than 6. So again, I'm going to, let me get back to the black. I'm going to say 2x is less than 6. And then I don't need to use additive inverse here because I already have all variables on one side and all constants on the other. So what I do need to do here is a little bit of division. This is telling me that 2 x's have to be less than 6. So to find out what 1x must be less than, we divide by 2. And we find out 2 divided by 2 is 1, so we have 1x there. And that has to be less than 6 divided by 2, which is 3. And we get to graph it. So again, I'm going to put my boundary right in the middle. My boundary is 3. That is where my solutions either make this statement true or untrue. And since 3 is not a part of my solutions, I'm going to have that be an open dot. And then all numbers less than. So like my student pointed out, we're going in this direction on the number line because that matches the symbol. So all of these. So that's going to include 2 and 1 and 0 and -1. It is not going to include 4 or 5 or 6. So this is a two-step inequality, meaning we're going to need 2 steps to solve it. Oh my God, can we do it? Yes, I believe we can. So we are looking at 3x minus 7 is greater than or equal to 13. All right, 2 steps. So first thing, let's get all of our constants to the same side of the inequality. So we need to do additive inverse. We have a negative 7 there, so to make a 0, we're going to add 7. We're going to add 7. Whoops, why did I put 17 there? Add 7. So what we're left with then is 3x, we made a 0, is greater than or equal to 20. All right, so if 3 x's have to be greater than or equal to 20, then we can divide both sides by 3. Divide both sides by 3. That's going to tell us that x is greater than or equal to 20/3, which we can go ahead and put that into a mixed number if you prefer, and it'll actually be much easier to graph as a mixed number or as a decimal. And so 3 goes into 26 times, and what we're left with would be 2/3. Okay, let's graph it. So how are we going to graph this fraction on a number line? And we're going to do the same thing. It might seem a little bit tricky, but we're going to do the same kind of thing. We know our boundary is between 6 and 7. So I'm going to put 6 on my number line, and I'm going to put 7 on my number line. So 6 2/3, there would be 6 1/3, and there's 6 2/3. Now this is 6 2/3 is included in our solution, so we're going to have a closed dot at 6 2/3. And then our solution is all numbers greater than or equal to. So greater than or equal to. So we're going to fill it on in. And then lastly, in order to check that our inequality is true, we can do a couple of things. So since we're saying that x is greater than or equal to, I'm actually going to take my 20/3 and I'm going to replace x. I'm going to go back to my original inequality. I'm going to say 3 times 20/3. And again, if you would rather use a decimal for this, that's fine, but you know how I feel about fractions. I love them. Minus 7 is greater than or equal to 13. Why I love this is the same thing as just saying, 3/1 times 20/3. So boom, you just got 20. So I can just call that as 20 minus 7 is greater than or equal to 13. Go ahead and simplify. 13 is greater than or equal to 13, and that is true. It is true for the or equal to part. 13 does happen to be equal to 13. Hurrah! So we don't always want to use that boundary point because it's not always equal to. So let's check another solution in our set. So 7 would be true, and 8 should be true, and 9 should be true, and 10 should be true. Let's try 10. Why not? 10 should be a part of our solution. So again, go back to my original inequality and replace x with 10. So I'm going to say 3 times 10 minus 7 needs to be greater than or equal to 13. 30 minus 7 needs to be greater than or equal to 13. And indeed, 23 is greater than or equal to 13. So we are happy.